We were talking transfer function. Transfer function. This is a part of my control systems course. Module 2. I will call the transfer function here G. This is all in the Laplace domain. It's this ratio of output over input. And here's sort of the key relationship. The output is the product of the transfer function and the input. R is the input, Y is the output, G is the transfer function, all in the Laplace domain. To get what they are in the time domain, you would need to do inverse Laplace transform. So that's that basic relationship. And I wanted to introduce, we're still doing definitions. We did characteristic equation, poles, zeros. Now we'll talk about the prototype, first and second order systems. And I'll tell you why in a second. But we looked at some physical models already. This first order system up here was a result of a mass damper system that actually didn't have equilibrium, but it was first order, meaning the differential was a first order differential equation. You can also look at this denominator, and the highest order of S is its order. So this is S to the 1, so it's first order. This was the mass spring damper system equation. See this 2, second order. If we just rescale them to normalize, and I'll talk about why we normalized them that way in a minute, a little bit later. These are the transfer functions for the prototype first and second order system. Now there's multiple reasons we want to look at these guys. One, we can look at these particular transfer functions and characterize outputs for certain standard inputs. Inputs like an impulse, a step function, a ramp, a parabola, a sinusoid, all that stuff, and have generic results for those things. Secondly, many more complicated systems, transfer functions, can be approximated by one of these guys, the first or second order prototype. Kind of a third reason is you'll get an intuitive feel for sort of standard outputs when we see graphs, et cetera. And finally, these parameters, this tau, this zeta, this omega sub n, they will come to have physical meaning. This tau is a time constant. This zeta is a damping factor, damping constant. Omega sub n is the natural frequency. These will all, you'll learn where they come from and why we give them those names, why they have those interpretations. So we'll be working a lot with these two guys. So it's kind of doing definitions. Here is that basic relationship. Output equals transfer function times input, right? What if the input in the time domain is an impulse, meaning a Dirac delta function, a single bang, bing, like tapping a mass spring damper with a hammer? Well, the Laplace transform of a Dirac delta function is just 1. You put 1 here, you just get the transfer function itself. Meaning the impulse response, or the response to an impulse, is the inverse Laplace transform of the transfer function. So the transfer function has kind of yet another meaning. And if we go on, there's a Laplace transform property. If you multiplication in the Laplace domain is convolution in the time domain. So this relationship here, y equals g times r or r times g. In the time domain means either this convolution or that convolution. And in this context, this little g, which is the inverse Laplace transform of the transfer function, is called the weighting function because it says how to weight the input in this convolution integral. So there's kind of related things that will have different names. Transfer function, the impulse response and the weighting function are the same things. Happen to be the same thing. So sum that up, we have two ways to find an output to a system. We can either do the Laplace thing, which says multiply the input, the Laplace transfer of function, the Laplace transform of the input times the transfer function, and then take the inverse Laplace transform of that result. So there's a lot of Laplace transform stuff, or evaluate the one or the other convolution integral. Depending on the problem, one of these is more easy or convenient than the other. Don't worry, you're not going to have to do a whole lot of that. And this stuff is, well, sometimes you're working in the Laplace domain, sometimes in the time domain. Let's do one problem kind of end to end. We have this truck pulling this cart with a spring and damper between them. We're tasked to find the transfer function between their velocities, where we treat the truck's velocity as an input and the cart's as an output. We'll assume they start in equilibrium and at rest. So they're both at time t equals 0 or just before times t equals 0. The truck is just sitting there, the cart is just sitting there, and everything is in balance. There's no motion. And okay, so let's get started. We'll call the truck's displacement from its equilibrium as r, like an input. We'll call the cart's displacement from its equilibrium as y. So then we'll do our mechanical modeling. F equals ma. M is the mass of the cart. A, acceleration, is the second derivative of this guy's displacement. And there are two forces on that guy, the spring and the damper. The spring will be proportional to the difference between these two displacements. The force of the damper will be proportional to the velocities at the two ends of the damper. The velocity of the cart and the velocity of the truck. So there's the F equals ma equation. If we get all the y stuff or the output stuff on the left and the r or input stuff on the right, here is our math model. There's our differential equation, our math model. Take Laplace transforms. Every derivative is a multiplication by s. You can do that. And here then is the transfer function. Still second order, but now we have an s in the numerator that we weren't seeing before. If we plug in these numbers for the mass, the spring constant, and the damper constant, we end up with these numbers. So here's the transfer function. But these are displacements. The cart displacement, the output, over the truck displacement, the input. We were asked for the transfer function between their velocities. Well, here's velocity is just the derivative of displacement. So the Laplace transform of the truck's velocity is just S times R of S. It's a Laplace transform of the displacement. Same for the cart, you just multiply by S. So if I want the transfer function of the velocity of the cart over the velocity of the truck, it's that S big Y over S big R, the S is canceled, and I have the same transfer function that I did between displacements. And here it is where we now have the denominator in monic form. So that's an exercise in both mathematically modeling a mechanical system and finding the transfer function. That's where I'll stop this video.